Alright, so we are still working on double integrals over general regions, and on this example we want to evaluate, but we want to evaluate the integral by reversing the order of integration. There we go. Now, the integral that we are given is first integral is from 0 to 8. Innermost integral is going to be the cube root of y all the way to 2. And the integrand is going to be x to the 4th plus 1. And then we're going to have dx dy. Now, when we're looking at this integral, it's going to be very important that we try to extract the equations that we're working with, in other words, the bounds that we're looking at for that region. So let's start off by extracting those bounds. So first we're going to annotate here that the x values are going to be bounded between the cube root of y and 2, and we're also going to have the y values being bounded between 0 and 8. Now, naturally this gives us 4 different equations that do the bounding for that region. The 4 equations are these. Cube root of y is equal to x, and x is equal to 2. We have y is equal to 0, and we also have y is equal to 8. So these are the 4 equations that we're looking at to do the bounding. Now, my suggestion is take some time now and try to sketch that region yourself. All right.
So when you're looking at that region, this is what we have so far. I have here that on GeoGebra that I had graphed x is equal to the cube root of y, y is equal to 8, y is equal to 0, x is equal to 2, and we get this nice region inside. Now, the way the integral was given to us was that it was taking horizontal heights first, because if you notice the innermost integrand was from the cube root of y to the upper bound of y is equal to 2. Now, if we want to change the order of integration, then naturally we're going to need to eliminate those initial parameters or bounds, and we need to then restructure our bounds to be these vertical heights. Now, that means that taking these vertical heights, we're going to need some values, in other words, some y values to go from 0 up to this y value. In order to do that, we then need to solve this equation for y. So we're going to keep going with that process.
So now that you've sketched a region, I'm going to show you a quick sketch on GeoGebra as to what it should look like. So now that we have that region sketched out and we see the region, we're going to reverse the order of integration. Now, as you're going to see, switching the order of integration is not as straightforward as Fubini's theorem. Right, Fubini's theorem was applicable because we had this rectangular region that we were integrating over. And in this particular case, we don't have a rectangular region, therefore Fubini's theorem does not apply, but we can still find the same integral if we work through it by reversing the area of, or the order of integration. So instead of having my x's change in horizontal height first, I'm going to have my y's change in vertical height. That means that we then need to develop some functions for y that are in terms of x. So what you do here is you take your first equation, the cube root of y is equal to x, and you solve for y, making this y is equal to x to the power of 3. Now, by looking at your picture, you're going to see, okay, well, I have this y is equal to x to the power of 3, and that's then going to create my heights that I'm looking for. So vertical heights for your y values are going to be from 0 to x cubed, And then all of those vertical heights are going to change for every single x value between 0 to 2. And here we see now we have this integral where if we want to take the integral here, this is going to be quite nice because evaluating this iterated integral, the innermost integral first, notice that the square root of x to the fourth plus 1 is a constant as we're going to integrate with respect to y. So when we integrate, we'll get y times the square root of x to the fourth plus 1 evaluated from 0 to x cubed with respect to dx. Now, making this evaluation, we will get the integral from 0 to 2, and we're going to get x cubed multiplied by x to the power of square root of x to the power of fourth plus 1 with respect to dx. Now, it's at this point in time that we can see, hey, as long as we make a substitution, a good substitution, say u is equal to x to the fourth plus 1, that means that du is going to be du is going to be 4x to the power of 3 dx, then we can see our u substitution will work. Now, I leave it up to you to show that the rest of the process will yield an answer of 1/6 multiplied by 17 to the power of 3/2 minus 1. All right, and that's your example.